Yes, nice, nice. All right, well, sorry about that. Okay, so lithosphere, heat flow, and possible evidence of activity. Okay, so what we're going to start talking about is the lithosphere. And, it's not the crust, which is a compositional layer, it's a mechanical layer. And there's different kinds of lithosphere. There's elastic, mechanical, and thermal. So there are a lot of different definitions. Oh, that's still not it. Oh, that's it. That's it. That's it. Yes. All right. Excellent. All right. Woohoo. Next, please. Oh, am I advancing? I'm advancing. Okay. Okay. Yeah. And, this might be kind of a, for atmospheric people, why do we care about the lithosphere? It's just super important. It controls the surface deformation. It's really a strong control on volcanism in terms of the depth of pressure release melting. And it has a big effect on convective regime. And so you've heard some of these things already this morning. And it's really been tied to the theories of how Venus has resurfaced and level of geologic activity. Some of the talks this morning talked about the idea of Venus being in a stagnant lid and how that was initially part of the idea that Venus catastrophically resurfaced and then had little or no geologic activity. So we'll come back to that at the end. So a few definitions about elastic thickness. Obviously, it's the part that supports loads elastically. The mechanical lithospheric thickness supports loads through both the elastic and viscous strength of the lithosphere, and that's a strain rate dependent thickness, so that introduces some uncertainty. And then the thermal lithosphere, it's basically the part of the outer shell that doesn't convect. And so it, extends down to a greater depth than actually the part that supports loads. And heat flow is a super simple equation, right? It's just the thermal conductivity times the thermal gradient. And, there's some debate about what the best thermal conductivity value is. We've used 3. And the real question is, what about thermal gradient? So we'll talk about that next. Okay, so I'm going to give you the results and conclusions up front, and then we'll talk about how I got there. So we looked at heat flow and elastic thickness from 89 different features. 75 of these estimates are new. Some are from prior studies. And what we found for these specific features is that the average elastic thickness is about 11 kilometers, and the average heat flow about 100 milliwatts per meter squared, with some big ranges in there. So one of the interesting things that we did beyond just getting these estimates is compare them to a global map of elastic thickness from gravity and topography. And in general, they agree pretty well. The values from flexure of the topography are pretty local. They occur on hundreds of kilometers length scales, but the global estimates of elastic thickness, they're done over a couple of thousand kilometers. So these values agree reasonably well, and I'll show you that. And so implications, most corona form on areas of thin lithosphere. Where's Pat? And many corona frequently cluster along, many corona, which are often found along rifts, have similar values to active terrestrial rifts. And we saw some high heat flow values for the rifts in the previous talk, or the one before that. And the agreement between the global and the local lithosphere give us these values of about 40% of the planet having thin lithosphere, elastic lithosphere on the order of 20 kilometers or less, about 40% having thicker, 20 to 50, maybe larger in terms of the elastic thickness. And then we have tessera, which are crustally compensated, so don't really fall under the elastic compensation, or areas that we just couldn't resolve in the gravity. So these lead to kind of new interpretations, this agreement between the sort of local and the more regional values from gravity. In a previous study, we interpreted the high heat flow at corona as largely due to thinning of the lithosphere, which may occur at some level, but I don't think that's the primary reason that corona give high heat flow values. In this previous paper. Oops, sorry, I get kind of got a little scrambled there, but in the previous paper where we looked at global elastic thickness, we offered two interpretations. One, that these thin values actually were isostatic crustal compensation, compensated by density variations rather than mechanical thickness. But the fact that they agree, the mechanical thickness agrees with the gravity maps leads us to interpret these as an actual thinner lithosphere, not crustal compensation. Those two can be, are equally good interpretation, but for most areas, I think this, where we've done these measurements, this indicates that we do actually have significant areas of thin lithosphere, tessera are largely, I believe, crustally compensated. Okay, so just a really quick cartoon to look at. This is from a paper by Burhoff, illustrating both the yield stress slope, the brittle ductile parts of the lithosphere. So, basically we're looking at bending of the lithosphere, and we have elastic deformation at the surface and brittle support, or sorry, ductile support of that bending lithosphere at depth. And the reason we can turn these into heat flow is that from studies of the Earth, people have demonstrated that the depths of the mechanical layer, the brittle plus the ductile support of the lithosphere bending, that temperature occurs, that thickness occurs at a temperature of between 600 and 800. So if we can find this mechanical thickness from these models of bending, then we can turn that into a thermal gradient. And that's basically how we get heat flow. So so we use a temperature of 770 C for these for depth to the base of the ductile layer based on assessments of the rheology, the strain, and kind of a guess of the strain rate, really. So this is the basic approach to getting heat flow. Okay, and just super quickly, a thinner lithosphere bends at a shorter wavelength than a thicker lithosphere. So this plot of the coherence versus the wavelength at the top for gravity just shows that we can get this kind of information from gravity, because a thicker lithosphere will produce a different gravity signature as a function of the elastic thickness. Due to, when you look at it, the gravity and topography in the spectral domain, you can see the effects of different thicknesses in terms of where the signature falls off. I didn't do that, but okay, we'll move on. So why corona? Somehow volcanoes are missing the boat when it comes to flexure on Venus, perhaps because they are largely on thicker lithosphere. But in any case, we have been able to get a lot of estimates of elastic thickness at corona just because they have these topographic rims, and they lend themselves to the modeling of the bending from which we can derive the elastic and brittle, elastic and ductile thickness, and thus get heat flow. So that just shows you the topography there, and we take these profiles and model them to derive these values. Okay, so here are the results. Elastic thickness is across the x-axis. On the right y-axis, we have heat flow, and then thermal lithospheric thickness on the right side. So the stars are the heat flow estimates. And there's a big range of these heat flow estimates. Some of them are fairly low as you go to larger elastic thicknesses, and Artemis is even on here. It goes out to 45, 50 kilometers elastic thickness. So the arrows on the far side there are the range of values that are estimated for the Earth in the blue, continents in light blue, oceans in dark blue. The average Venus corona there is in red, and at the bottom is some prior models of Venus stagnant lid, or kind of a typical Venus stagnant lid heat flow estimate. Some of them are moving up to higher values, maybe 75 or so. But in general, you can see that the stagnant lid models are lower than many of the values that we find. And, we typically hear the average values for Earth's oceanic crust, for Earth's continental crust, for the Earth. And it's not so, simple on the Earth. There's a lot of big range of values. And on Venus, we also have a big range of values. And as I said, many of these occur near rifts. And they are, very comparable to these areas of active rifting. The high values are the active rifting areas on the Earth. And I believe the high values that we're seeing here are active rifting on Venus as well. Oh, yeah, so I didn't say too much about the thermolithospheric thickness. It's probably a lower bound because we kind of assume a linear thermal gradient, which is not what we really see on the Earth. So these are probably a lower bound on the thermal thickness, which is, the thickness of the lithosphere that you hear about in convective models. Okay, so here's this map of elastic thickness from Anderson Smrekar. It looks crazy, right? And I think that's what it's telling us is that there's a big variability on a small spatial scale in many places in elastic thickness. And the low values there, 10 to 20 kilometers, are what we saw at most of the flexural estimates of elastic thickness. And we also saw some in the range of that high middle area. I'm not sure, there's another paper out, Jimenez Diaz, which kind of gets a similar range of elastic thicknesses, but both in their work and here, the larger values tend to be bottom loading. And so, they may not be, they may be biased towards larger values. The only range that we were able to validate by comparing to the flexural results are the low and that should be medium there in the 20 to 50 kilometer range. And so, there may be larger values as well, but they haven't been validated by this independent approach. That's kind of going on a timer there. So, okay, so, but the other thing I'll point out is that, okay, so there's in the low range of from 0 to 20 kilometers, that's fairly contiguous, and there's about 40% of the planet has that low value, which is mostly what we saw with the corona estimates. Okay, so this is a map of that distribution, and the symbol shape shows the whether it's greater than the median value is 75 kilometers, 75 milliwatts per meter squared or not. And the color shows the agreement between the gravity measurements and the topographic flexure measurements. And in general, there was pretty good agreement between these values. In some cases, they did not agree, and the localized value higher. So maybe those are instances of the lithosphere actually being thin locally. And some we just couldn't assess that because the gravity resolution was so low, we didn't get a value. And this shows that, you have to take all these values from the gravity, with some caution, especially in these areas, which tend to be larger values of elastic thickness because the gravity resolution is so lousy. And, it's not fabulous for gravity work anywhere, but in these areas, you have to really have a lot of caution. Okay, so to come back to this point of the interaction between the lithosphere, geodynamic models, and resurfacing. As you heard this morning, for a long time, we simply focused on Venus being a static, low geologic activity, thick lithosphere. The green is the lithosphere. And people said, well, geodynamics said, well, that really doesn't work. You can't get enough heat out of a planet like Venus, with such big radiogenic budget. So it can't possibly have been in a stagnant lid forever. So that led to these ideas of episodic resurfacing, where you have cycling between a thick lithosphere and stagnant lid, perhaps sinking into the lithosphere, having thin lithosphere for a part of the time, and then eventually cooling and coming back to the system. And that was in part based on the idea of catastrophic resurfacing having happened 500 million years ago, and that could have been this event that got rid of the stagnant lid. And I know there are a lot of proponents of that. I personally am really a fan of this plutonic squishy lid on the right for a variety of reasons. It's consistent with the idea of regional equilibrium resurfacing, which I think there's a lot of geologic evidence that supports that as well. Well, it allows for variability in the lithospheric thickness on small length scales, as you see in the crazy maps of elastic thickness. Obviously, we have volcanism all over the surface in different length scales. And, from, I heard in Joe's talk and others have certainly modeled the ability of corona to cause delamination of the lower lithosphere. There may be some sites where subduction also occurs. So, for the observational evidence as well as, well, I guess basically I like this model because the observational evidence and it's consistent with the regional resurfacing model, which to me makes more sense than the catastrophic one for various geologic reasons. But it also, it works well with this idea of having high heat flow some places and lower heat flow other places. So thank you very much.